We continue our study of the point set topology of R, and today we will talk about a very important theorem in analysis, which is known as Bolzano Weierstrass theorem. Its proof depends on the axiom of completeness. Axiom of completeness axiom of completeness is something which helps us to obtain this theorem, and indeed, both these things are equivalent. If you assume one of them to be an axiom, then prove that the other holds. And we have assumed that this completeness is an axiom, and we call this Bolzano-Weierstrass statement as a result. But before for that, it's about the limit points and limit points of a set. And for that, we need to define limit point of a set. And what is the limit point of a set? Let me define. Let's take a subset of R and let C be a real number, any real number, which can be anywhere. It is not necessary that it has to be in B or outside B. It has the freedom to be anywhere, provided it satisfies the following condition. Then we call C a limit point of the set B if for every delta neighborhood and delta C of C, we have this thing that n delta C intersect minus taking out C from this interval, and this set must intersect B. This must intersect B. It is equivalent to say that this interval delta C contains a point, at least one point of B other than different from C, other than C. If you have such a situation, then this C is known as a limit point of the set B. So what do we have now? If you look at this following thing, let us look at some examples of limit points. Let us look at the, for example, first it would be better to begin with the set R, and you take the C be any real number. Then for any delta, for any positive number delta, we see that this C minus delta and C plus delta, this is a delta neighborhood, and it contains infinitely many points. So obviously it has points other than C also, and so indeed this whole of the interval lies inside R. That may, or you can say that clearly, and so clearly this delta neighborhood, which is the open interval C minus delta, C plus delta, minus C intersection R is non-empty. Indeed, this set from where we are taking out C, this is also known as deleted neighborhood. This is also known as deleted neighborhood of C if C is removed from this neighborhood. This is a subset of R, hence it has a non-empty intersection with R, and this implies by definition of C that C is limit point. see the limit point of R. See the limit point of RC was an arbitrary real number, and that means R is something in which every element in it is a limit point of it. So, but let me add also give you another name. People also call limit point. Limit point is also known by another name. Limit point is also known as accumulation point. Limit point of any set is also known as accumulation point. This is also known as accumulation point. Okay, this was another name. Let's look at some other non-trivial example. Let us look at this example. Yeah, let us take interval I, which is an open interval. So you have this interval open, and for example, if I take A to B, let us take for example, let us take A to be 0 and B to be 1. The process to determine its limit point is same whether you take A to be any number, B to be. You have 0 somewhere here, and suppose you have 1 here. Then what I want to tell you, that each point inside this interval is a limit point of this interval, and 0, 1 is also an interval of this limit point of this. But first, let us look at that whether 0, 1 is a limit point of this or not. And to show that 0, 1 is a limit, 0 is a limit point of this interval, I will write that 0, this set, this is closed interval, is set of all limit points of open interval 0, 1. Likewise, in case of arbitrary interval, then arbitrary open interval AB, and the closed interval AB will be the set of all limit points for this. But so let's verify it for this. First, let us take x to be any element in this closed interval, and I'm going to establish that this x is the limit point of open interval I, this set I. So we have the possibility. First, let us assume that x lies in the interval 0, 1. The case of x equals to 0 and 1 will be discussed later. Then you have obviously somewhere x is lying somewhere here. Okay, and so what then it implies? You see, then x is somewhere here, and whatever delta you choose, whatever large or small delta you choose, then what happens? If you choose whatever smallest possible radius you can choose, any interval here, something, then for any delta greater than 0, x minus delta and x plus delta contains points of interval 0, 1 other than the point x itself. How you going to prove that when x is here, you are going to have this? No, you have this situation. You have this situation. Let's write it in a rough way. You have 0 less than x less than 1, and delta is a number which is positive number. What do you want to do? You want to establish a number which lies in this interval x minus delta, but at the same time that point must be lying in the interval 0, 1. That number needs to be less than 1. That means we want y in this interval x minus delta, x plus delta, such that this y also belongs to this open interval 0, 1. Let me continue in the same page after clearing out these other things. Just okay. Let us first look at this. What situation do we have? What kind of y? How we are going to get that y here? We can make some certain guesses from the looking at the line. We have here 0, 1. I have x somewhere here. Okay, and there are infinitely many points. So now, since x is strictly greater than 0 and it is strictly less than 1, and there are infinitely many points, but that depends upon delta. Delta we have to choose. That we have to be very precise that exactly the point that lies in this delta neighborhood is also a point here. But then what I can say, there are infinitely many real numbers mm, between 0 and x. So I will call real numbers between 0 and means every real number between 0 and x of 0 and x of there are infinite real numbers in this of this interval 0, 1. Now now things are very clear. You have this interval x and you are approaching at some, let us take the bigger case that this delta is lying outside. Delta is something larger. You have all the possibility delta can be large also, and you have other possibility that delta can be small enough also. Let me choose the other color to indicate it. Delta can be somewhere. This can be delta also, delta prime. And so you have all the possibilities that delta is something that's small enough so that the interval lies entirely inside this 0, 1, or it crosses outside also. But when you look at 0x in particular, you're looking at this part. And whatever delta you are choosing, then that delta will have points to the left of x also, and it will have points in it to the right of x, so immediate to the right at that point. And definitely, when you look at this 0 at x, and you look at this intersection of this with x minus delta and x, and this is quite obvious that here this intersection and both these intervals whose intersection I'm talking about, both these intervals have a common right endpoint. If they are starting from a same endpoint, and they might be having different left endpoints, but they are having same right endpoint, so they start from the same place. So some part of this segment is common to both of them, and when it is common to both of them, their intersection is going to be non-empty. And if their intersection is going to be non-empty, then clearly this 0x interval being contained in 0, 1, and this other interval x minus delta being contained in x, the larger the neighbor delta neighborhood of x, and they will have a non-empty intersection. And with this, it establishes that this delta neighborhood of x contains points of the open interval 0, 1. So this proves that, and that this was an arbitrary delta. This proves that every delta neighborhood of x contains points of 0, 1 other than x, and hence this x becomes in this way R. cluster point are what you see it as a limit point of this open interval 0 1. Likewise, let us look at the case second, where we talk about whether 0 is its limit point or not. And the same argument will work for whether 1 is the limit point or not. Again, looking at the line, you see uh, any delta neighborhood of 0 must be of this form: 0 minus delta means minus delta, and 0 plus delta means delta. So clearly, there are points, or you must say that clearly this part 0 delta, this is a part of this interval minus delta and delta. This will be this is intersecting this interval 0 1, because the part of this neighborhood which is to the, yeah, this one, let me encircle this one, this part here. This is 0 delta. Delta can be bigger also, but anyways, the part to the right of this 0 is a part of the open interval 0 1, and hence it will always have non-empty intersection. And if it has the non-empty intersection, then clearly, surely, minus delta and delta intersection 0 1 will have non-empty intersection. And this, from this it follows that every delta neighborhood of 0 intersects this open interval 0 1 at a point other than the 0. But obviously 0 is not a part of open interval. Obviously, wherever it will intersect, it will intersect at a point which is different from 0, and hence with this you get to see that this 0 is also limit point of this set. And likewise, the same way we can argue for this 1 to be a limit point of. So with this, it proves that every point of, hence with this, I'm very going to be very brief here. I'm not writing everything here, just to move ahead. Every point of this interval 0 1 is a limit point, of open interval 0 1. So instead of writing every time every set of limit points, we give it a name. The name has a definition for a subset B of R. B bar is B bar be the set of all limit points of B. Then this set of limit points of B is called the closure. This is called the closure of set B. So it will be better to now refer to the that a limit point is nothing but it's the element of the closure of a set. And what is the closure? Closure of a set is set of all limit points of a set. As seen, we just saw in the previous examples that set of limit points of R is the R itself. Set of limit points is the R itself, because each point of R is a limit point of R. So closure of R is the R itself. And next, what we saw that the set of limit points of the open interval is the closed interval 0 1. That means the closure of the open interval is the closed interval. And with the same way, for any finite open interval, the closure is the closed interval. And indeed, for any closed interval, the closure is the set itself. This can be verified by using the same argument. Since we have already seen that set of all limit points, obviously A and B is also a limit point of this closed interval, as other points inside this interval are also limit points. You don't need to argue it in a different way. The argument works same way as done for the open interval 0, 1. The only thing that you need to establish, you need to establish, for example, in case of closed interval 0, 1, you need to establish that any point outside this interval is not a limit point. Is not a limit point, because any point that you choose outside of the open interval, that point may lie to the left of 0, or it may lie to the right of 0, right of 1. And if a point which is to the left of 0, you can draw an interval of this size, and this is a delta neighborhood, and here you can choose delta b. In this case, you can choose this interval to be x minus delta, x plus delta, and for delta to be a number which is half of the distance, or you call it a mod of x. This is the distance of 0 from x. And obviously, the radius of this half of the mod of x. And with this radius, this delta neighborhood of x clearly is not going to cross the 0 to the right side of it. And then this is a neighborhood which will have no point of this closed interval 0, 1. And this will establish that there exists a delta neighborhood of x which contains no point of the interval 0, 1. And with this cannot be a limit point of this set. And likewise, similarly, what you can do, you can choose in case of the any point to the right of 1. What you can do, you can draw again a delta neighborhood. You can always find a delta neighborhood, and let this delta neighborhood be something y minus, instead of delta, let me take y minus r, y plus r. Here you may take r to be some number, but you have to take it to be something. Let us take it to be 1/2 of the distance of y from 1. It is distance of y from 1. And obviously, when you are measuring the distance of y from 1, that this distance is equal to, here let me zoom at this, and suppose you have 1 here, and if I zoom at this thing, and suppose I get to see y here, and this is the distance, y minus 1. And obviously, when you are taking the half of the distance, you have here, you are here, and I'm just taking every point to the right, left, right of this here, and this side I can go at any stretch, and look at that. And then in this delta neighborhood, where I'm taking delta to be r, I have denoted it to be r to be mod of y minus 1 1 2. In that case, this delta neighborhood, or r neighborhood I call it, y minus r and y plus r, you see that every point in this delta neighborhood is at a distance less than or equal to less than r from the y. Every point here has a distance less than r. That means every point has to be to the this side or this way. No point, because any other point at this place, let me mark it with any point here, will have a distance larger than r. And so it can, this part will not be part of this interval, and hence if this not, it is no other part coming from a closed interval 0, 1 can be part of this interval. You just measure the distance, and from there it follows that this cannot be also a limit point of this interval 0, 1 closed interval. And the same way you can establish for closed interval as well as open. So here we have been able to establish closure of several sets. And the other observation, some of the observations that we observe here that needs to be in your mind, observation is that the first thing that we observe is that closure of a set is equal to B is possible. Is possible. Closure of a set is equal to the set itself is possible, as was seen in case of closed interval, its closure was the set itself. Such as sets actually are, we are not going to introduce, such as sets are precisely the closed sets. Closure of a set happens only equal to with the set itself in case of only closed sets. That means this holds only for closed sets. I'm not going to prove it. You don't require it, but you can keep it as a record in yourself. Another thing, we can see that closure of a set is empty also. And for this, I'm going to give an example you, and I'm going to prove it that closure of rational real numbers is equal to free. This is equivalent to say that set of natural numbers do not have any limit point. So we mean that the set of natural numbers n has no limit point. Let us argue in the other. Let us check that why it doesn't have any limit point. What to do? What to do to establish that it doesn't have any limit point? We take the first case two. We take the two cases. First, let us take a natural number, arbitrary natural number, and we will establish that this natural number is not a limit point of. That means no natural number is a limit point of this set of natural numbers. And you have the natural numbers here. And look at this. Suppose n is somewhere here. And its next in natural has to be n plus 1, and its predecessor has to be n minus 1. Okay. Now, to establish that some point is a neighborhood of some set, you have to check that each neighborhood of that point must contain a point of a set other than the point itself. But to show that it is not a limit point, what you have to do, you just have to find out that one neighborhood which doesn't contain a point of the set other than the point itself. So we are going to construct a neighborhood here. Now, let delta be equals to 1. Then n minus 1, n plus 1. This is a neighborhood. This is a delta neighborhood of n, obviously. Intersection n is n. That means this delta neighborhood contains no other point of set of natural numbers other than n. See how, suppose there is some, suppose there is some m in n such that m belongs to n minus 1 and n plus 1. What it means, it clearly means that n minus 1 is less than m, and this is less than n plus 1. Look at here, your elementary understanding of the natural numbers says that what it says, what you can say, how you can sum up this thing. Let me, how you can sum up this thing. Now, we have, let me like this, we have n minus 1 as predecessor of n, and n plus 1 is successor of n. n has predecessor, which is n minus 1, and n has a successor, which is n plus 1. But you know about natural numbers that if m is not equal to n, in case you say that m is not equal to n, see then what happens? From this inequality here, indeed, let us move a bit differently here. What this inequality implies? This inequality implies that minus 1 is less than m, minus n is less than 1. And what it implies? It implies that mod of m minus n is less than 1. Now here is a good thing to observe, that this says that the distance between m and n is less than 1. But you know that between any two natural numbers, the minimum possible distance is of 1. And here you are having this distance to be less than 1. That means they cannot be distinct, hence m has to be n. So this establishes that you don't have any other natural number lying in this delta neighborhood of n, and hence this establishes that this n cannot be a limit point of set of natural numbers. Likewise, let us take uh, x to be a real number such that x is not a natural number. Because for natural numbers we have already seen that this is not a for natural numbers we have already seen that this is not a and no natural number is a limit point of this. Now we have further two possibilities. Possibility one is that this real number can be less than 0. Then x and 0. Why to take x? Let us take this way. Suppose you have 0 here and you have x here, and this is the distance. Let this distance be delta, and let me go to this side also. This be x minus delta, and this becomes then the delta neighborhood of x. Then clearly this particular delta neighborhood x minus delta, which is and 0 up to 0. This is the delta neighborhood because we are, and this is the distance for delta is the distance from x to 0, and we are moving to its left also by the equal distance. And clearly this is a delta neighborhood where I'm taking this delta to be a particular number, which is the distance of 0 to x, and this is mod of x. So this delta neighborhood of x contains no natural number. Why it doesn't contain natural number? Because every element in this delta neighborhood is a negative number, and no natural number is a negative number. So for this case, there is always a delta neighborhood which contains no element of natural numbers. Hence, this cannot be a limit point of natural numbers. And the possibility second is that x is greater than or equal to 0, but x is not a natural number. So then there is a result that we did that we had proved in our one of previous lectures, that for any real number there exists an integer m, or indeed let me further try. Let me further to uh, yeah, it's okay. Let's do this. There exists an integer m such that m is less than or equal to x, and this is strictly less than m plus 1. Okay, but if we are taking x to be greater than or equal to 0, and in case you have this possibility now that x lies to the right of 0, and you have the first natural number 1, and in case x lies somewhere between 0 and 1, and if it is not equal to 0, the clear case is that somewhere x here is, then you will have a natural number. One of the natural number has to be 0, because m and m plus 1 are consecutive integers. And if x lies somewhere here, then if x lies in this interval 0 and 1, uh, it cannot be equal. Then clearly m has to be 0, and then you will have this situation, uh, m which is equal to 0 less than equal to x less than 1, and in that case you can always draw this interval. You can have this interval 0 1, or you can go or 0 1 is contained. Yeah, let me move to the next page, and then in that case we can choose a delta neighborhood of x. I have to go up to this distance. This distance is 1 minus x. This distance is 1 minus x from 1 to x, and this is mod of x, and let this be delta. Then the neighborhood delta x, which is x minus delta move will be the number which is to the left of x, and to the right of x we are moving up to x minus plus delta, and x plus delta is going to be equal to 1. And in this neighborhood, this is the delta neighborhood of x, and every number here is less than 1, and every number here is less than 1. Let me write this in this delta neighborhood, every number is less than 1. So, so this delta neighborhood x cannot contain any natural number. So this intersection is empty, and hence in this case also x cannot be limit point of this set of natural numbers. Now finally we have the last possibility when x is greater than 1, then applying the result, the existence of natural number, then you will have a natural number m such that m is strictly less than x is less than equal to m plus 1, because now m cannot be equal to x. We are taking x not to be a natural number, then the m and m plus 1 being consecutive number implies that this m is also a natural number. It can be at more at the minimum m can be 1 now, and it implies that this neighborhood m plus 1, this is a now neighborhood of this is the neighborhood of x, and this is a neighborhood of x. This may not be a delta neighborhood, because you might have a situation here x here, you might have m here and m plus here, but we can choose a delta neighborhood. So we can choose this to be something delta here, and this any delta neighborhood inside this a open interval m and m1 is a neighborhood which contains no natural number. Indeed, because this neighborhood m with left hand point m and right hand point m plus 1 contains no natural number. It has empty intersection, and hence any delta neighborhood uh, which lies inside m and m plus 1 contains no natural number, and with this with this we establish that set of natural numbers has no limit point. with the same argument on the same lines, you have to establish this thing. I will leave it as it is very easily verifiable that any finite set has empty closure. Has empty closure. That is to say that a finite set has no interior, has no limit point. For that means this exercise will imply that if a set, that means that if a set has a limit point, if this set cannot be finite, that means if a set has a limit point and it cannot be finite, then it has to be an infinite set. Then it is an infinite set. So this is one of the consequence of a set having a limit point, because finite set has no limit points. But this is not the complete thing. Now, and also at the same time, we saw this is the same time. At the same time, we saw that not every infinite set has a limit point. Not every infinite set has a limit point. As we just say, for example, we just saw that set of natural numbers has no limit point. You can see that set of integers also has no limit point. Now, there is a result important that is known as Bolzano stuff that I told you at the beginning. And this gives us at least a one class of infinite sets. It guarantees the existence of limit point for a one class of infinite sets, and those infinite sets are bounded infinite sets. And I'm going to write here now this Bolzano-Weierstrass theorem statement, and it states that a bounded infinite set has a limit. This is so simple that a bounded infinite set always has a limit point. So this is a sufficient condition for a bounded infinite set to have a limit point, but it doesn't imply that if a set has a limit point, it's bounded or it is bounded because of it is a set having a limit point will always be an infinite set. This is what I discussed in the remark. But it doesn't imply that a set having a limit point is always going to be a bounded. For example, let us look at this example. Uh, this interval 0 infinity uh, has limit points. Has limit points, and what are its limits? This is an open interval. Every point lying in this open interval is a limit point, including 0 is also its limit point. It has limit points, and it is not bounded. It is not bounded. So what we want to tell you is that a set which has limit points may not be always bounded, but bounded infinite set always has a limit point. And the other thing that that remains to be told about unbounded sets, and that is that unbounded sets, there is no certain condition which guarantees you the existence of limit points for the unbounded sets, because there are unbounded sets which have limit points, and there are also unbounded sets which do not have limit points. This example which I show, that open interval 0 infinity, it is an unbounded set, it has limit points. At the same time, set of natural numbers is also unbounded. It is also unbounded and infinite, but it doesn't have, right? And has no limit points. Has no limit points. So this is all possibility. This is all that we have possibility, and but it is quite uh, suggestive and recommended that you must try to find out limit points of good number of sets. And the important set, one of the simplest set that I want to tell you is that this set 1, 1 by 2, 1 by 3, so on. has only one limit point. We have to find which limit point, one limit point. So why I am telling this example? I'm telling this example that number of limit points of sets can be any number. There are sets which have zero number of limit points. There are sets which have finite number of limit points. There are sets which have infinite number of limit points. That means this number of limit points, this number can range from, it can be finite. There are sets which have finite number of limit points including zero. There are sets which have infinite number of infinite number of limit points, and within infinite number of limit points there are sets which have only denumerable number of denumerable number of limit points, and there are sets which have uncountable number of limit points. It is good that you just get in touch with each of these sets. For case of finite, you can give this example. For case of uncountable number of limit points, for example, you see that the set of limit points of this open interval is the whole of the closed interval, and this closed interval is an uncountable set. And you may work on this, that a set which has innumerable number of limit points. They have infinite number of limit points, but they are not uncountable. So with this, we have the end of this here.